Kia ora and welcome to video 12 in the series Delightful Differentiation. This video today is a related rates problem. It involves a spinning circle or a point moving around a circle, and then this point here moves inwards and outwards as the point A moves. So the first question asks us to find the angular velocity, d alpha dt, which is the rate that this angle alpha is changing. In the question we're given d theta dt. We're told that the point P, the wheel is rotating anti-clockwise at a rate of 360 RPM, revs per minute, not to be confused with radians per minute. And the second question asks us for the velocity of the pin P dx dt. In other words, the horizontal change as P is moving along the axis here, x will initially be decreasing as A moves away, and then there'll be a point where x starts moving backwards. Or in the case of the x-axis, positively. So we need that expression dx dt. We're given it here, we just need to prove it. All the best for this problem, and we'll catch you after the intro music for the solution. Okay, so this is a related rates problem involving circles and triangles. We are going to use the sine and the cosine rule from level 2 trigonometry. If you're an NCA student, you may have skipped that. Those formulas are on the formula sheet when we get to them. If you're unfamiliar with the formulae, then have a look on the formula sheet and see that they're there. Okay, we've got a spinning wheel rotating at 360 revs per minute. It has a radius of 40 centimeters, and AP, the length of the rod, is 1.2 meters, 120 centimeters. Be careful with units. The pin P slides back and forth along the x-axis as the wheel rotates. Okay, so that makes sense. If A moves anti-clockwise and it's further away, then P is going to be pulled in towards the origin, and vice versa. As A gets closer to its starting position, then the rod will extend past where it is currently. It will go out that way. Find d alpha dt, the angular velocity of the connecting rod, in radians per second. So we've got to be careful here because, again, units, we've got 360 revolutions per minute. So we need to convert that into radians per second. Okay, to find d alpha dt, we need to connect d theta dt to the d alpha dt, so related rates. Using the sine rule first, we can look at triangle OAP and write down that sine of theta over 120 is equal to sine of alpha over 40. So the sine rule applies if you have a pair of sides that is opposite a pair of angles. Actually, I should rephrase that differently. You have a side and an angle opposite, and then you have another side and an angle opposite it. Then you can apply the sine rule. So if we were to differentiate this, we've got options, but theta and alpha are both functions of time, so it makes sense here to differentiate implicitly with respect to time. So if I take the derivative with respect to t of both of these things, what are we going to get? Well, the 120 and the 40 in the denominators do nothing, they're just constants. Sine of theta, when I differentiate it with respect to t, I actually differentiate with respect to theta, so I have cos theta, and then I multiply by d theta dt. Okay, so that's implicit differentiation at work. And then on the right hand side, differentiating sine alpha over 40 with respect to t, I differentiate with respect to alpha, so cos alpha over 40, but then I multiply by d alpha dt. Okay, to find d alpha dt, which is what the question is asking us to do, I just need to substitute in values of alpha and theta and d theta dt. Okay, so be careful here, d theta dt is not 360 revs per minute. In the units that we're using, we need to convert into radians per second. So 360 revs per minute is the same as 6 revs per second, and then 1 rev is 2 pi. So if we're looking at the units here, d theta dt, and we're in radians, then revolution is 2 pi, so we've got 12 pi radians per second. Okay, and then when theta is equal to pi over 3, we can use the sine rule that we had earlier before we differentiated it to work out what alpha is. Okay, so that's this formula here, and theta is equal to pi over 3, so we've got sine of pi over 3 over 120 is equal to sine of alpha over 40, and then at pi over 3 there is a special angle. It's on your formula sheet as well, the special triangles. We have pi over 3 there, which is 60 degrees, and this is root 3, 1 and 2. So the sine of pi over 3 opposite over hypotenuse is root 3 over 2. So we get root 3 over 240 equals sine alpha over 40, or sine alpha is equal to root 3 divided by 6. Okay, and if you look back to the derivative expression, we don't need to know what alpha is, we just need to know what cosine of alpha is. Likewise, we didn't need to know theta was pi over 3, we want to find the value of cosine of theta. So substituting the information we've got into that expression, the related rates expression up here, cosine of theta, well, theta is pi over 3, cosine of pi over 3 is a half, so we've got a half divided by 120 times d theta dt, which was 12 pi, and that equals cosine of alpha. Well, we know sine of alpha is root 3 over 6, that's another triangle we can draw. Sine of alpha, root 3 over 6, opposite root 3, hypotenuse 6. Use some Pythagoras to work out that the adjacent side there is 36 minus 3 square rooted, so square root 33, and therefore if we continue substituting into our related rates equation, cosine of alpha is root 33 over 6, all divided by 40, times d alpha dt, the rate that we needed. Okay, bit of rearrangement here, so a half divided by 120, all times by 40, we're ending up with, just making sure I'm doing my maths correct here, 40 divided by 2, 20, 1/6 times 12 pi equals root 33 over 6 times d alpha dt. Cancel the 6's off, we've got 12 pi divided by root 33 in radians per second. Second part. Express x, the length OP, in terms of theta, and hence show that the velocity in centimeters per second of the pin P is given by dx dt equals blah. So now we're considering this point P here, and we're saying how fast is x changing? So how fast is it moving in and out of towards the origin as the wheel spins around? First up, they're very kind, telling us that we need to express it in terms of theta, but I think that's kind of obvious that the thing that's changing here in this problem is the point A is moving around, and that's dependent on the angle theta, and we know that we've got some angular velocity to take into account. Okay, we're going to start off by using the cosine rule for this. So we have a triangle, x, which we'll call OP, is this length here, and now we've got three sides of a triangle, x, 40 and 120. We've got two angles, but we only need one. There's a couple of ways that you can do this. I feel the easiest way to do it when you've got the cosine rule, I'll just write the cosine rule as c squared is a squared plus b squared minus 2ab cosine c. If you're trying to find an expression for x in this case, which would make more sense if we had that side opposite that angle. The problem is the side x, we don't have the angle opposite it. We could write an expression for that. I guess 180 minus theta minus alpha. But if we want to avoid bringing in another angle and then therefore another rate, I'll avoid bringing in another angle and we'll switch the use of the cosine rule around a little bit. So I'll go 120 squared equals 40 squared plus x squared minus 2 times 40 times x times cos of theta. So I've switched, saying the angle that I want to bring in, theta, because it says in terms of theta, is opposite the 120. So I'll write 120 there and I'll write theta there. The problem with this is it brings in the quadratic formula, which can get a little bit messy. Okay, so 120 squared minus 40 squared. No, we're trying to make x a subject here. Okay, so we've got x squared minus 80 cos theta x, and then we've got plus 40 squared minus 120 squared equals 0. So it's a quadratic in x now. And we can make x the subject of that. X equals minus b, so 80 cos theta plus or minus b squared minus 4 times a times c. No, a is 1, my bad. A is not negative 80, minus 4 times 1 times c, which is 40 squared minus 120 squared, all over 2. I believe if you simplify that down, you end up getting 40 cos theta plus or minus 40 square root cos squared theta plus 8. Okay, does that make sense, that expression? I think we actually just need the positive root. Yeah, if we look at that, x is 40 cos theta is this side. Let's just change colours so we can see it. 40 cos theta is the adjacent side of that triangle, and then x will be bigger than that, so we're adding on, and therefore change that to a plus. Okay, that's x in terms of theta as the question asked for, and then dx d theta is the derivative that they wanted. So we've got 40 cosine theta differentiating to minus 40 sine theta, and then we've got to use chain rule for this part. Turn the square root into a power of a half, and differentiate the outer function. The half comes down the front, halves the 40, cos squared theta plus 8 to the power of negative 1/2, and then multiply by the inner derivative, which we have to differentiate cosine squared theta. It's more chain rule because it's cosine theta all squared. 2 times cos theta to the 1 times by the inner function differentiated, which is negative sine. And then if we tidy this up, minus 40 sine theta plus the 20 and the 2 there, so another 40. It's a minus now, given there's a negative in that last term. And then it's all divided by the square root of cos squared theta plus 8, negative 1/2. Drop it down to the bottom as a power of 1/2. So, is that the expression we wanted? Not quite, because you can see that there's a factor. Oh, of course. Sorry. We wanted dx dt, and we've just found dx d theta. So we now need to times this by d theta dt. D theta dt, we had that from the original problem. It was 12 pi radians per second. Okay, so therefore dx dt, and there's a common factor of minus 40 sine theta in this expression. So I can factor that out. 1 plus cos theta over that, all times by 12 pi. That's going to give a minus 480 pi out the front of the sine theta. And yes, that's what we wanted.